Hello everyone. Today I would like to talk about a fascinating and essential topic in algebra using zeros to graph polynomials and understanding how the shape of a graph behaves near each zero. So you might be wondering, why is this important in our life? The truth is, polynomials are everywhere. They model the trajectory of rockets, describe the motion of the waves, and even predict the ups and downs of the stock market. And understanding their behavior helps us make a sense of these patterns. So, moreover, in fields like engineering, physics, and data science, being able to sketch a polynomial graph can provide insights into system dynamics and solutions to complex problems. I will. So today I'll explain the concept of zeros, the role of multiplicity, and how to predict the shape and behavior of a polynomial graph. Along the way, I'll share visual examples to bring these ideas to life. So let's start with the basics. A zero of polynomial is a value of x the polynomial equals where the polynomial equals zero, essentially, where the graph touches or cross the x-axis. These points provide a roadmap for sketching the graph of any polynomial function. We can find the zeros of the polynomial for various types of polynomials using various methods that are discussed below. So for linear polynomial, for quadratic polynomial, and for cubic polynomial. So for linear polynomial, finding zero is the easiest of all, as there is only one zero, and that can also be calculated by simple manipulations. So after equating polynomial to zero, here you can see the example, like f of x equal 2x minus 7. And by doing these manipulations, you can find that the zero of the polynomial. So for quadratic polynomial, there are various methods to find roots or zeros of a quadratic polynomial, such as splitting the middle term with a discriminant or using the Vieta's theorem. So here you can see the example 2. And we will solve it with Vieta's theorem. So, and the zeros are 3 and minus 5. So for cubic polynomial, to find zeros of this, there are many ways, such as rational root theorem and long division together. So one method of finding roots of cubic or any higher degree polynomial is as follows. Step 1, use the rational root theorem to find the possible roots. And if a polynomial has a rational root, it must be the division of p and q, where p is the integral constant and q is the leading coefficient. So I'll show you these steps and you can understand it easily. So step 2, after finding one root, divide the polynomial with the factor formed by that root using long division and write the polynomial as a product of quotient and dividend. So step 3, if the quotient is a quadratic expression, solve it by the methods above mentioned for quadratic polynomials. And step 4, the result of step 3 is the required factors, and by equating the factor to 0, we can find the zeros of the polynomial. So in a simple way, I can say that we just factorize the polynomial. So here I also provide the example. And you can see how we factorize a polynomial. So first of all, we find the possible zeros. Then we use the long division term with -1 0, possible zero. And we can find that -1 is a real zero. So we write down this with x quadratic x plus x minus 6, and then we see that it is the quadratic polynomial, and then we just find the zeros also with Vieta's theorem and find out that zeros are -1, 2, and -3. So but I want to mention that here's where it gets interesting. The behavior of the graph near these zeros depends on something called multiplicity. By understanding multiplicity, we can predict whether the graph will cross, touch, or bounce off the x-axis at each zero. So you can see the theorem. If P at x is a polynomial of degree n, then P at x will have exactly n zeros, some of which may repeat. So multiplicity tells us how many times a zero is repeated in the polynomial. It directly impacts whether the graph cross, touch, or bounce off the x-axis at each zero, as I said. So here's a breakdown. If the multiplicity is odd, like 1, 3, 5, and etc., the graph crosses the x-axis at that zero. If the multiplicity is even, like 2, 4, 6, 8, and etc., the graph touches the x-axis and doesn't cross. Instead, it bounces back. So let's visualize this with two examples. So you can see P of x where x minus 2 in degree 3. The zero is 2 and a multiplicity of 3 is odd. So the graph crosses the x-axis at 2, but the crossing is cubic shaped, flatter and curved. So in other example, when the degree is 2, that means it's even. Here the graph touches the x-axis at 2 also, but bounces off, creating a parabolic shape. So by simply observing the multiplicity, we can predict that the graph's behavior at each zero. While zeros determine the local behavior of the graph, the overall shape is governed by the leading term. So the leading term comes from the highest power of x. Here's how the degree of the polynomial affects the end behavior. So you can also see the examples. First of all, if the degree is even and the leading coefficient is positive, both ends of the graph point upward. You can see in the example where we just took the simplest example where x powered 2. So you can see just the parabola. So if the degree is even and the leading coefficient is negative, both ends point downward. Also, just the simplest example, just to show how it works. Just minus x in quadratic minus x. If the degree is odd and the leading coefficient is positive, the graph falls to the left and rises to the right. You can see. Also, the simplest example, like x in degree 3. And the last one is if the degree is odd and the leading coefficient is negative, the graph rises to the left and falls to the right. You can also see that. So, in conclusion, understanding zeros and their multiplicities not only demystifies polynomial graphs, but also empowers us to see patterns and solve problems more efficiently. Next time you encounter a polynomial, approach it with confidence. So I want to say that finding zeros and knowing how it works make our work simpler, make graphing polynomials simpler, and understanding these graphs also simpler. So you can intuitively graph the polynomial of different examples of polynomials just by finding its zeros. So it's really important topic in algebra, and thank you for your attention. Good luck.